Yay.
So I'll first go through some small part that we're supposed to cover, which is density-based clustering. It should be pretty straightforward. So I'll just kind of go through the slides, but if you have any questions, stop me. And then we'll spend most of the time on the Gaussian mixture models. And so this is, I think in week 4, there's like this DBSCAN thing that I think Bayan was looking at. And so this is the density-based clustering algorithm. So let's just talk about it real quick. Okay, so we'll do overview, basic concepts, DBSCAN algorithm, and then analysis of the algorithm. And I haven't like gone into depth. There's like, I linked an article in our syllabus that you can read about this. And I haven't read it yet, so I didn't have time to read it because of all the Gaussian mixture model stuff. But yeah, you can read it if you want to like know more. But yeah, so the basic idea is that we know that clusters are going to be like these dense regions in the data. And so we can kind of like detect which areas are like densely densely populated, yeah, and where there's a lot of points close to each other, and we can define clusters there. And so the clusters are going to be defined as a maximal set of density connected points, which we'll define later what that means, density connected points. And it can detect arbitrarily shaped clusters. So they don't have to be like circles or squares or anything. It can just be, yeah, they can be arbitrary shapes. And so there's the method, which is DBSCAN, so density-based spatial clustering with of applications with noise. I don't know who came up with that, but like I said, there's an article on that. Okay, so now we'll go through the basic concepts. So the basic idea is that you're going to be looking for like these, these like regions of high density, and you're going to try to cluster those high density points together. And so you'll define 2 parameters. One is epsilon. And epsilon is kind of like a maximum radius of your neighborhood. So you basically are defining, okay, how much, so this epsilon says how far away from, like how far away from one point can another point be to still be in that cluster. Like, so it's kind of like a distance measurement. And then the minimum number of points, the min point is the minimum number of points in the epsilon neighborhood of a point. So you define some parameter that says, okay, there has to be X amount of points for this to be defined as a cluster. And so these are the 2 sort of main parameters, and we'll go into depth on them, but that's kind of the parameters that we'll define. And so then high density is defined as an epsilon neighborhood. So this distance, epsilon neighborhood of an object. Epsilon neighborhood of an object contains at least the minimum number of points that you defined of objects. So for example, if min point is 5 and epsilon is 1 centimeter, Q has high density here, and point P has low density because there isn't, 5 points in that 1 epsilon or 1 centimeter distance from P.
Yeah.
Okay, and then we'll do a few more definitions as well. So we'll define core points, border points, and outliers. So given those 2 parameters, epsilon and min points, you can categorize the objects into 3 exclusive groups. So a core point, a point is a core point if it has more than a specified number of points, the min points, within epsilon. And these are points that are at the interior of a cluster. And so, yeah, I think the idea here is not necessarily like k-means where you have like kind of like a center point, but you're basically just trying to see if, so this core point is not necessarily like a center point from k-means. It's more like, Yeah, it's kind of hard to. Let me think
It's
about
just
how.
like, is it in the defined circle?
Yeah,
Like
it's
in
in
the
the yeah, it's in the definition. Yeah,
right.
yeah, yeah. Thank you for that. Yeah, it's in the definition that you've made. And then a border point will have fewer than min. So yeah, so for example, this is like a core point here, and then a border point will have fewer than the minimum number of points within epsilon, but it's in the neighborhood of a core point. So like this border point here, you can see it doesn't have 5 min points within 1 unit of epsilon, but it's within 1 core point. I mean, it's within epsilon of 1 core point. And then a noise point, I guess in this case an outlier, is any point that is not a core point or a border point. And that's sort of one of the points there. So I'll skip that. And so this is an example. So these are the original points here. And here you can see the core points in green. And the border points. And so this isn't all one cluster. So it's not like I'm clustering all the core points, but it's just saying that all these points are satisfying this definition. And then there's some border points that are like satisfying the definition of border points, which is like at least within 1 core point. And then there's some outliers that aren't satisfying either. Okay, and then we can define some density-based related points. And so we define, I guess, some terms, I guess. So we define direct density reachability as when an object P is directly density reachable from an object Q if one, Q is a core point, and 2, P is in Q's epsilon neighborhood. So this P point here is direct density reachable by point Q. Okay. And then we have density reachability. And so that says a point P is density reachable from a point Q if there is a chain of points P1 through Pn such that P1 equals Q and Pn equals P, such that Pi plus 1 is directly density reachable from Pi. So we're basically using that the sort of first definition to define this density reachable region. And so that's basically, yeah, I think you can think of it as like, you can form a link between, so you can say P is density reachable from Q because I can form a link of points that are directly density reachable all the way to P. Does that make sense?
Yeah.
Okay. Okay. And then density connectivity.
Sorry, what's the difference here between density connected? So is density connected the only difference is that you need to have multiple, you need to span multiple points that are satisfied density reachable?
Yeah, let's see. So a point P is density connected to a point Q if there's a point O such that both P and Q are density reachable from O. So that means you can go either way, right?
Oh, I see. Okay.
Yeah, so like if you start at O, yeah, so P and Q are density connected if you can start at O and get to either one of P and Q by using directly density reachable points. So you're using O to define a relationship between P and Q. Okay. Yeah. Okay. So those are some definitions, and then we'll talk about the DB.
Wait, can you go back? I'm sorry. To density connected. Okay. Okay, I see. Thank you.
Okay. And I guess he did some example here, but we'll skip that. And then we'll talk about the DBSCAN algorithm. I'm not going to, let me think about, okay, I guess I do have to read it. I actually don't know how it works, but we can figure it out together. I'm assuming that you just use
there
those.
might be an overview below this.
Okay.
Maybe not.
Yeah, maybe not.
You can also look at the visualization. It's just not very readable to look at this code.
Yeah, but I think you can intuit at least what it's going to do.
Mm-hmm.
Looks like you're sort of visiting points and then marking neighbor points, and then choosing which points to enter into the cluster or not enter into the cluster. Yeah, so maybe we can click on this and see what happens. I don't want to do that.
You essentially are looping over every data point and seeing if it's a core point. If it's a core point, then you see if all of its border points are core points. And then if those are core points, then you look at those border points. And then if those are core, it just propagates a cluster as long as you have that density, direct density reachability, which forms a cluster. Once you break the chain, then you look at another point that you haven't looked at that isn't in a cluster yet.
Mm-hmm.
And then you continue to propagate with that one. You look at its border points, and then those border points look at their border points until you have distinct clusters.
Mm-hmm.
So
Yeah,
is it recursive?
It feels recursive.
I'm not sure. I'm sure it is.
Yeah, it feels recursive because you kind of are going back. You're kind of like recursing back to like, so you select all your core points and then you go in and you come back and then you go in and then you come back. Yeah. So I see it feels recursive. But yeah, so I guess some analysis of DBSCAN and
the visualization's not gonna work.
I still think
do you want to see it?
Yeah, I still think you should look at it. It's pretty quick.
Okay, let me see if I can pull it up. I think I'll just put it on my browser. So let me share the whole screen. What kind of data would you like?
Pick this smiley face.
Okay, so we're going to do epsilon of 1, min points of 4, and see what happens.
Yeah, that should be fine.
Okay, so it seems like it's just expanding from some start point and finding core points and then expanding the cluster as it finds more core points.
But it's interesting. There's like two different, processes happening.
Yeah, that is interesting. They're going to merge at some point. It seems like. Will that happen?
Probably not, right?
Yeah, they do merge. So you probably have to have like some condition for like merging if you need to merge.
I think once you finish your cluster, you start two new ones. I think that's all that happens.
Oh, right, because it started from one cluster, in the red cluster, right?
Mm-hmm.
And it just expanded in two directions.
Mm-hmm.
And that's fine. You can just keep adding points to the cluster.
Yeah.
Okay. So that's cool. So let me go back to
That's really cool.
this. Okay, so now some analysis. So apparently DBSCAN is sensitive to the parameters that you choose, so the epsilon and the min points. So I guess here we see differences for min points at 4 and epsilon at either 0.5 or at 0.4. And so you can see that the results are kind of different depending on which one you choose. Here's another example of those. Okay, and then so kind of to look at what happens. So if you have epsilon of high value, so you have a large sort of space that you're looking over for the clusters. So the clusters will merge, and the majority of the data points will be in the same cluster, whereas maybe they're not necessarily that close to each other. And so like when we think about these epsilon, I think last time, Stuart, you talked about like different sort of distance metrics, and depending on like sort of the dimensionality of your vector. So this epsilon, we're kind of thinking of it in like 2D space right now, of like how far away things are, but this can be like a variety of different sort of like distance measures that you take into account when you're defining this epsilon, depending on the data set and the features of the data set. So then if you have low value, you'll have a large part of the data that won't be clustered and considered as outliers because they won't classify the number of points to create a dense region. And then do we define the number of clusters in DBSCAN? And the answer is no. So it's not like k-means where you like set the number of clusters that you want sometimes. We just allow it to do what it does, and it finds the clusters. For min number of points, so if you choose min number of points as 1, every point will be a cluster on its own. So you need at least at least more than 1. And then let's see, min points 2. What's getting at here? When you have, basically you'll get a cluster for each 2 points that are epsilon away from each other. So min points should be at least 3. Okay, so I guess this is just making an argument that like you shouldn't do 1 or 2, you should at least do 3 number of points. Rule of thumb, min points is d plus 1. I'm assuming d is the dimensionality of your vector. But I'm not sure.
I'm assuming that too.
Yeah.
Yeah, your features, your dimensions of your data.
Yeah. Okay. So how about epsilon elbow effect? The idea is that that for points in a cluster, their kth nearest neighbors are at roughly the same distance. Okay. Noise points have the kth nearest neighbor at further distance. Okay. So the plot is sorted, plot is sorted distance of every point to its kth nearest neighbor. So here we have 3,000 points and x-axis shows just the point index. Point indices are sorted in ascending order based on their 4th nearest neighbor distance. I'm not sure what this is getting at here, actually. Points.
3,000 points. And the x-axis shows just a point index. Basically,
So similar to the elbow method we looked at for k-means. It's just going to help us determine some parameters.
Okay.
no, I'm so confused. So you make a plot like this for every, because this one's the 4th nearest neighbor. Would you do that for a lot of different numbers? You look at 3 and 4 and 5 and 6, and then that helps you. Okay.
Yeah. So for k-means, we just had to do one elbow plot looking at the loss for each k. But here we have 2 parameters. So what you need to do is have a plot for each choice of min points, for example, and then this plot would help you determine what epsilon should be. So what was that distance where you start, or that number of points where you start getting diminishing returns.
Yeah, okay, so this is like the distance here, and this is the number of points. Okay.
So we want to look at the point. We want to choose the elbow where.
So would you want to choose the epsilon to be like something like here or something? Like where it starts to sort of go away? That's kind of what I'm thinking.
Well, it says elbow effect, right? So don't you want to do like higher up, like 10?
So you're thinking like here? Well, let's see. Yeah, because where do you? Yeah, I guess you're right. Because I guess this is where you do start getting diminishing returns, right? Or not, or like increasing anymore. Increasing distance anymore here will just like sort of ramp up the distance.
Yeah,
really
I think
high.
you start to include the outliers if you go higher than 10.
Mm-hmm. Okay, that kind of makes sense. So I guess I guess you would choose the min number of points to be somewhere in this region, and note that like your distance epsilon would be around 10 for that.
Yeah, like you're gonna, I guess your epsilon, if it's below 10, it captures this number of points, and you're only missing, was that 500 out of 3,000? Okay.
Yeah, okay, that makes sense. Elbow effect, another example. So this is showing distance and k order. So I'm assuming k order is the number of points. That's into the 5.
I think so. That don't make no sense. K order.
Points often does not have significant impact on clustering results. Interesting.
K distance.
This is the same thing we were looking at before. When they talk about K distance, I believe they're talking about the K nearest neighbor distance, which is equivalent to what we saw above. There's just multiple plots on one figure.
What's K order?
Oh, okay. So this K order is the like minimum points that you're going to choose?
I don't think so.
No, because the min points are up here.
That's so each line or each curve corresponds to some midpoints. The bottom is just the y-axis is distance. That means x-axis must be your points then. Okay, it's not super clear. Not super clear. I wouldn't stress about it as long as you understand generally what you're supposed to do.
No.
Okay. So when it works well, it's robust to noise and can detect arbitrarily shaped clusters. So this is sort of going back to that original image, and you can see the different clusters here that it's chosen out of. When it doesn't work well, it can't handle varying densities, sensitive to parameters, hard to determine the best setting of the parameters. So if you have the original points here, and you might want it to cluster as such. Let's see, yeah. So if you set min points to be 4 and epsilon to be this, then you'll get a clustering like this. So you have this, and then this whole thing is one cluster. Versus if you set min points to be 4 and epsilon to be
yikes.
Very that's so interesting. Yeah. So then all these are like one cluster. Is that true?
I think those are all outliers.
Oh, they're all outliers. Oh, okay. Yeah. And then you just only have these. Oh, interesting. Okay. Yeah. So I guess you would want all these to be clustered together, right? Well, I don't know. It depends on.
Yeah, it looks like the above one got it right, but the below one,
yeah,
we got it wrong.
Yeah, this depth of cluster. Okay, take home messages. The basic idea of density-based clustering. Yeah, so the basic idea is, I guess, density-based clustering. The two important parameters we talked about. So we talked about two important parameters, definitions of the neighborhoods and densities in DBSCAN. We talked about core, border, and outlier points. We talked about DBSCAN algorithm, and we talked about DBSCAN pros and cons. Okay, we'll stop there for any questions before we move on to Gaussian mixture models.
I think this made a lot of sense. This feels like directly useful, and I'm thankful.
That's good. Yeah, I would recommend maybe even taking an hour to read the article. Might provide some more examples and insight.
Okay.
And we have the like Bayan showed in the group. We have the tutorial for DBSCAN, so maybe also take a look at that.
Sorry.
Okay. So, Gaussian mixture models. Okay, I thought this was funny.
Wait, was that in the slides?
Yeah.
Oh no.
He has memes all over the slides. Wait, where's the later lectures?
Oh man. Okay, so we'll do an overview, and then we'll talk about the Gaussian mixture models, and then we'll talk about the expectation maximization algorithm. Okay, so as a recap so Gaussian mixture models are going to use like probabilities like crazy, because it's like a probability based, it's like probabilities on top of the probability of the Gaussian. So it's really interesting. But yeah, so we're gonna talk about first a recap of these conditional probabilities and Bayes' rule. And so remember that we can represent a joint probability AB as conditional as the product of the conditional probability of A given B times probability of B, and I'll talk about this in a little bit, but or probability of B given A times probability of A. And so just as an example of how this works, if I have some like data here, and this is kind of what we did in the probability lecture, so some data here of some observations, and we want the probability of A1, the joint probability of A1 and B2. So we know that the joint probability of A1 and B2 is really just A1, B2, so 3 over the total number n, so it's 3 over 23, right? So P A1 B2 is 3 over 23. And so here I'm showing that I can write that as the conditional probability of A given B2 times the probability of every of all the B's. And so that's written as sorry, not A given B2, but A given B, given that B2 happened, and the probability of B2 total. So what that looks like is I'll take the number of instances of A1 and B2, which is 3, divided by the total number of times B2 happened, which we'll call X2 here, which is 9, X2, so this is our XJ column, and I'll multiply that by the total number of times B2 happened, so, or the probability that B2 happened, and so that's 9 over 23. And so you can see here that, you know, it's just the product rule, and you cross out the X2s, you'll get the same thing that we had originally, which is probability of A1, B2. And similarly, we can write it the other way, where we write, okay, the probability of seeing A1, B2, so that's 3, divided by seeing A1 in total. And so we'll just look at this first column A1, and we'll take 8 here. So that's our y1. And then multiplied by the probability that A1 happens, right? So A1 happens 8 times out of the total 23 times. And so here we can see the same thing that will get the probability that we want. So you can represent either way. And so from that, we get Bayes' rule, which says that the conditional probability of A given B is equal to the joint probability of A and B divided by probability of B, which just comes directly from this. Or we can write that as probability of B given A, and I think this is sort of the key Bayes' rule thing. Probability of B given A times PA, which is just the joint probability divided by PB. So it's interesting because when you look at it, if you just like didn't look at the third or the center term here, and you just looked at the end terms, they kind of look like, oh, how do you get that? But when you kind of do the math, it kind of makes sense. And then the last thing here is just kind of
really quick. We read the first part, probability A given B. That's the vertical line.
Mm-hmm.
Okay, thank you.
Mm-hmm. And then here, I think we're just showing the probability of A being 1 or being A1, right, is just the probability, the joint probability of A being 1 and B being anything, basically, right? So we sum over all B's. So this I is like basically all B values. And you can see that from, you know, the data, right? So if I want A1, probability of A1, then I'll just sum over everything that is B. It doesn't really matter what B is. And that's the probability that I have divided by the whole number of instances. And so I can also write that as by kind of using some of the same stuff that we just talked about as the probability of A given BI times probability of BI over all I, right? Over all I instances. And so that's 2 ways to get probability that A equals 1 or A equals A1. Okay, so as an example of that, this is a pretty simple example, but we'll kind of go through it anyway. So you have some data here. I guess another example of that. There's some data here. You have today and rainy, that today's rainy, today's cold, tomorrow's rainy, tomorrow's cold. So you want to find out the probability that tomorrow is rainy. And that's going to be equal to the sum of all, or I should say the probability that tomorrow is rainy given, or the probability that tomorrow is rainy and, how am I saying this? Joint probability of tomorrow and today for tomorrow being rainy and today being everything. So today being rainy and cold. I didn't say that well, but I think it'll describe more down here. So, I mean, just intuitively, you can just see, okay, the probability that tomorrow is rainy is just this plus this, right? Like, and that's the probability that tomorrow is raining. But if we want to write that out in like math terms, then we have the probability that tomorrow is raining and today's raining, and that's 4 out of 9, plus, so there's a sum over all today being raining, or all of today. So plus the probability that tomorrow is raining and today is cold. So we just sum those two and we get 6 out of 9. Okay, and so to motivate Gaussian mixture models a little bit more, there's this idea that as we've talked about in these different methods that we've talked about, so the k-means, hierarchical clustering, and DBSCAN, we talked about how those can be difficult to do. So they all have like little flaws that we've pointed out in the various lectures that we've done. And so now we're trying to move towards sort of like a soft assignment, or soft clustering is what we're calling it. And so k-means, we made like hard assignments. So we basically said that each object is going to belong to only one cluster. You can't belong to more than one cluster. You only have one, and that's it. And I think similarly for the DBSCAN, you're either like in a cluster or you're an outlier. Stu, are you falling asleep?
Yes, I am. I was hoping you would notice. You're doing great though.
Okay. So so k-means you have a hard assignment. This is really interesting stuff. If you can stay awake, I would recommend it. It's really interesting.
Oh, it looks fascinating. I remember.
Yeah. But anyway, so you have our hard assignment with k-means, but with mixture modeling, what we're trying to do is like do a little bit of a soft assignment. So instead of assigning one data point to a particular cluster, or either it's in the cluster or not, we're trying to do like a probability that it's in the cluster, and that gives us a better a better way to sort of do do like real world sort of data modeling and data analysis, because it's unlikely that like there's this prescribed, so you have some data point that says, oh, like this either came from the fridge or it did not come from the fridge. There might be some, that's a bad example, but but there might be some sort of like probability that it came from the fridge, depending on how cold it is, maybe measuring temperature or something like that. So there's some probability in real world events, and not necessarily these hard assignments that we usually do.
Yeah, and it seems to be better on handling outliers.
Yeah.
Makes more sense.
Say that again.
I think it makes more sense.
Yeah. Okay, so then we'll talk about the Gaussian mixture model. So recall the Gaussian distribution. It's given by, so this px is our probability density function, and it's given by, so we usually, I guess, write it as this n of mu and sigma, where sigma is the standard deviation and mu is your mean, and this is the probability density function here. And then if you want to think about, a data point that has d dimensions, it's not just one data point, but is a vector of x equals x1 all the way to xd, then you can define your Gaussian as kind of the same thing. The only differences are like this d here. So now you're taking the d over 2 root, or I guess root of this 2 pi, and then the square root of your covariance, the determinant of your covariance, and then your exponential looks like this. So everything's just vectorized. And so now you have your mean. So if this is, I think, for a two-dimension model, so you have your mean at 0, 0, and your covariance is given by some numbers here. So just, I guess, in the book, I noticed that this is also called the information matrix. And then the inverse, which is used in this exponential, is called the precision matrix. That may be useful if you're reading and you sort of skipped around, but that's what they're referring to when they talk about these things. Okay, so then mixture models. So then what we're trying to do with the mixture models is create basically a weighted sum of a number of Gaussians, or a number of Gaussians, a number of normal distributions. So so let me just read this. Formally, a mixture model is the weighted sum of a number of PDFs, so probability density functions, where the weights are determined by a distribution pi. And so basically you have some probability density function, px, for some, so the probability of some x observed is going to be the sum over all these normal density functions at x, or like evaluated at x. So you have f0, which has some mu 0 and sigma 0, and then f1 has some mu 0 and sigma 0. And so you can kind of look at it in a 2D plane as this, like you have some Gaussians, and you have like basically different Gaussians, and then so when you're summing over them, you also weight them by some pi. So here, this first Gaussian is weighted by pi 0 and pi 1, and so on. Does that make sense? Okay.
Yeah.
And then we also define some constraints. So one constraint is that the sum of all the pi's, all the weights, has to be equal to 1. And this comes from our constraint that the probability density function, the integral over the probability density function, has to be equal to 1. So if we look at the probability density function px and we integrate over all of it, we'll note that as we integrate over every Gaussian over all x, so these pi's are constants, right? So as we integrate over all these Gaussians, we'll get that, this Gaussian gives you an integral of 1. The F1 Gaussian gives you an integral, or gives you a sum of 1. So this is equal to 1 when you integrate over all, and then so on for all of these. And so at the end, you'll get just px. If you integrate over everything, px is just equal to all the pi's, all the pi values, the weights. And so you have to have that the sum of all the weights, px is equal to the sum of all the weights. And so you have to have the sum of all the weights has to be equal to 1. And so that's kind of the rationale behind this constraint that you have here. Okay, so then generally sort of we can describe this P of x for the Gaussian mixture model as the sum over k of pi I times fi, where fi is some Gaussian. Okay. Okay. So then go ahead.
Well, I'm trying to understand why we have all these summed together, but I think you're getting there.
Yeah, maybe I should motivate a little bit more. So you might have multimodal distributions. So so like you might not be able to represent your data. So you might have some pieces of data. So I guess the clustering is like a good way to think about this. So if we have some clusters like this, if our data looks like, like things are like kind of clustered together, we know that Gaussian distributions are pretty common in nature, and we might want to represent this as some Gaussian distribution with some mean and some standard deviation. But we know that just one Gaussian is not going to represent this data, because we can see that there are these sort of like pockets, right? And so we can instead use like 3 Gaussians in this case, or like however many clusters you want to represent the data, and each of them is like a mode of the full probability density function.
I see. So each Gaussian represents a cluster, essentially.
Yeah.
Okay.
But it gives us the potential, or I guess it gives us the potential to not strictly assign 2 clusters. We can probabilistically assign 2 clusters.
Right.
Okay, I see what's happening. And we're kind of defining this Gaussian mixture model. It kind of reminds me of when you take a bunch of sines and you sum them up such that it matches whatever frequency you're at. You know what I'm talking about?
Mm-hmm.
I think it's the same thing, but with data points and probability.
Yeah, I think it can be thought of like that.
And it's basically like you're effectively getting, like, however many like clusters you want, you're getting these probabilities for a data point being assigned to any of the clusters.
Mm-hmm.
And so when you actually are summing up the probabilities for that one data point belonging to all individually each cluster, they'll all sum to 1.
Mm-hmm.
Right.
Mm-hmm.
That's not bad.
Yeah. You guys are right on it. Yeah. Okay. So some notes. One question I'll ask is, do you think the summation of a bunch of Gaussians is a Gaussian itself?
Wait, isn't it just a constant? It's one.
No, but not. I guess from a probability density function perspective.
I don't know actually, because isn't the idea that the more and more data points you have, eventually those data points will form a Gaussian? Like, isn't that like that's the central limit theorem?
Mm-hmm.
And so, if you're summing points that fall in a Gaussian distribution, and you're summing multiple different types of like Gaussian distributions, I want to say that it would end up being a Gaussian as well, with enough data points.
Yeah. So go ahead, Stu. What do you think?
Well, I mean, if they're all the same mean, then like I would imagine the hump gets bigger and bigger.
Mm-hmm.
But if they have different means, so they're like different humps, I feel like as you sum them together, wouldn't they go to a constant value? Or maybe it is just an uglier Gaussian that's distributed.
Actually, you might be right, Stu. That might create an outlier where.
No, I think you're right. I think you're right, Bea. I think it is a Gaussian. It's just an uglier Gaussian with like a different mean and tails.
So I should preface this by saying I don't actually know what the answer is, but I've thought about this. I've thought about this more than you all have. So I think I have an answer.
Okay.
And so I think that it's not this. I think the sum of a bunch of Gaussians is not a Gaussian. I think that the sum of we know that the sum of a bunch of Gaussian random variables is a Gaussian. But my intuition, and so that comes from, let's see if I still have it up here. No, I don't.
Well, even this image is a good example.
Which image?
If you go down.
The ones where you scribbled in, like you filled it in.
Where? Here?
Keep going down.
It was in the other slides.
Oh, this one.
Okay, here?
Yeah, like here. You see like pi represents distributions. And so if you're like joining these distributions together. And so if you look at it like this itself, if you try to draw your own like distribution for the sum of all of these, this wouldn't be a Gaussian. Like,
yeah.
The outlier of pi1 having a higher peak than the other ones, and so it wouldn't fall.
Yeah, and I think I would also just look at this, like this definition of what a Gaussian distribution is. And so I think that like if you took the product of all of them, then you would have a Gaussian, because you would just basically, so when you are taking the product of an exponential, you just add, the exponentials together. But if you're adding exponentials, then I don't think you would get like another exponential that just looks like this.
Yeah.
Sorry, I kind of dozed off a little bit, but I think the answer to that question is maybe. Can you hear me?
Yeah, we can hear you now.
The answer to that question is maybe. It depends. Because I believe two independent Gaussians sum up to a Gaussian. So it depends on if it's independent or not.
Okay, so you're saying independent, you mean that they don't cross over at all?
Right. Yeah, that makes sense, I think.
That does make sense. Well, I don't know. I think
I agree.
Yeah, I don't think I agree, actually.
Because think about the definition of independent, right? Like a Gaussian itself is a spread of Gaussian random variables, right? So that those two like being independent means that like the probabilities of it falling in line, like the random variables falling within a certain distribution, are independent of the other distribution. And so like if you try to sum them together, you could your central limit theorem applies again, or like then your overall like distribution would fall under a Gaussian, because they're not dependent on each other. Any singular variable is not dependent on the other.
I can send y'all some information on this. There's some text from MIT that covers this pretty well.
Thanks. This is.
Yeah, it's a very interesting thing to think about, because you have like the random variables themselves, and then you have like the Gaussian as a thing. And
Yeah.
but anyway, okay, so we'll just keep it moving. Some definitions here also. Px is a probability density function, but it's also called a marginal distribution function. So remember that for like a marginal distribution, if you have like joint variables or joint distribution pxy, then px is a marginal distribution across all, y's, right?
Oh, that makes sense. I was confused about marginal distributions.
Wait, can you say that one more time?
So px is or this last part. So if you have a joint distribution pxy, then you can take the marginal distribution of just x as of just x as the sum of. Does that make sense?
Yeah, it's what you were saying before, and when you were walking us through basic probability stuff. You're saying the probability of getting some value x for any y is going to be x, and you sum up all the different possible y's.
Yeah.
That's your probability for x.
Yeah. And so in this case, x would be called a marginal distribution. But in general, it's a probability density function.
Okay.
Yeah. And then px equals the density of selecting a data point from the known probability density function. So, and that data point being x, right? Which is created from a mixture model. So in this case, we have some probability density function that's created from a mixture model. But we're just taking one point x, right, and saying, okay, what is the density of selecting a data point, this data point from the probability density function?
Okay.
And then also we know that the area under the density function is equal to 1. So that has to be the case for every single density function. Okay, so mixture models are generative, and what that means is that we are dealing with a joint probability, pxz. So to kind of explain this, so we have pxz, and we're going to call these z's what we call latent variables. And I actually thought that it might be a good idea to just read the section. I think it does a better job of like explaining what these z's are than I can. So I'm just going to read it out loud here. Okay, so it says, let us introduce a k. So I'm reading from like right here. It says, let us introduce a k-dimensional binary random variable z. So binary meaning either 1 or 0, having a 1 of k representation in which a particular element z of k is equal to 1 and all other elements are equal to 0. The values of z of k therefore satisfy that z of k is either 0 or 1, and that the sum over all k of z of k is equal to 1. And we see that there are k possible states for the vector z, according to which an element is non-zero. Okay, and then we can define a joint distribution, p of x of z. So x is the same Gaussian mixture model that we were talking about earlier. And z is now this new variable. In terms of a marginal distribution, pz, and a conditional distribution, px given z, corresponding to the graphical model in figure 9.4. Let me see if that, I don't like these models actually, it doesn't really help. So we'll just keep going. Then the marginal distribution over z is specified in terms of the mixing coefficients pi k, such that p of z equal to 1 is equal to pi k. So basically the way I think about this is that Z is just like an assignment variable. So it's basically saying that like, okay, I'm assigning this particular X or something. So by giving it 1 or 0, and when you give it 1, I'm assigning this particular X to the cluster or the Gaussian K. So there's K Gaussians, and I'm assigning this X variable to this Gaussian. And the probability that I assign that Gaussian variable to cluster K, or the probability that I assign that data point to cluster K, is given by the probability pi K. Does that make sense?
Yeah. Yeah.
Okay, Stu, what doesn't?
So you're assigning, some element of your vector, some element X, some value Z.
Not quite. So I guess actually this might be. I think there's
I think a numerical
here.
example would help, where you like show the vector X. That could be like
Yeah, so I think this is what I'm going to show here. So there's basically, so if you have like these observations x1, x2, x3, all the way down to xn, and you have these clusters, K1, K2, and K3, or these Gaussians, I should say, K1, K2, and K3.
Yes.
So basically what I'm saying is that if you think about Z, if I was writing like some assignment in terms of Z, if I wanted to assign x1 to this cluster K1, then this would be 0, 1, 0.
Right.
Okay, but then what I'm actually doing is I know that like basically that I want to assign this. So I can basically do this for x1 in all these different ways, in k different ways. So 1, 0, 0, and then 0, 0, 1. But what we're kind of saying that Z is doing is simply just assigning these probabilities to K1. So when I say that like this is 0, 1, 0, what I'm basically saying is that the probability that X1 is assigned to K1 is just like pi of K1. If that makes sense.
Where pi is the weight for each Gaussian K. Okay.
So then that would give me that like the probability that I assign yeah, so like the probability that Z of K of that cluster is equal to 1 is equal to the pi of K.
And I see Z is, there's a different Z for each X. Right. The probability of, it's a joint probability of X and Z, where given this X and this assignment, maybe just keep going.
yeah, maybe I'll keep going and it might make sense later. So, and then we also talked about the parameters, where the parameters of pi of K must satisfy that it's, in between 0 and 1, and altogether the sum of them over K is 1 in order to be valid probabilities. Okay, so then I don't know how important this is, but I'll just keep reading. But because Z is a 1 of K representation, you can also write this distribution in the form P of Z is equal to the product over all K of pi of K raised to the ZK. So the way to interpret this is that because that Z is only going to have a 1 in one place, right? A 1 in the place where it's assigned, only one of these pi K's is going to be activated in the product. So like you basically have, let's say Z, let's say there's K, Sorry, it's really large. Yeah, let's say there's k, let's say k is equal to 3 or something. And so your product, your PZ is going to be equal, and let's say, okay, ZK is, or Z of 3, yeah, or ZK, how do I say this? Okay, yeah, I guess basically what I'm trying to get at is that this thing raised to the ZK means that it only gets activated when K is equal to, when K is equal to, okay, let me write this as this. So probability that Z equals ZK is equal to pi raised to 0 times pi raised to 0, let's say Z3 equals 1 or whatever.
Interesting.
And times pi raised to the 1, right? And so you'll only get one of these when Z activates that pi.
Oh, interesting.
So you can write it as this. But it's not, that's not super crucial. But so similarly, the conditional distribution of X given a particular value for Z is a Gaussian, where the probability of X given ZK is equal to 1, given that it's activated at K, is just the Gaussian at K, right? So the particular cluster that you're looking at with mu K and sigma K, which can also be written in the same form where you're raising these to the ZK. So all these are just gonna, all the ones that it's not, it's just gonna be 1 times the actual value. So it's just one, it's just gonna reduce all the other Gaussians besides the one that you care about to 1. Okay, so given that, let's go back here and kind of go through this. So you know that Px is equal to this, just the sum of the Gaussians times their weights, and we can write those Gaussians as just this n of x. Well, yeah, this just represents a Gaussian that has mu 0 and sigma 0 as its parameters. And so furthermore, you can write that in the summation as this. And what we're going to do now is we're going to write this PDF here as the probability of Z given K. So basically the fact that it's assigned to this K means that it has probability density function of that has parameters mu K and sigma K. And this this weighting is just the marginal probability of ZK. Yeah, so basically the marginal probability that that X is somehow assigned to this K. Okay, and from sort of Bayes' theorem and the stuff that we talked about earlier, we know that this product is just the joint distribution of X and ZK. And so if we sum that over all K, we know it's going to be equal to 1. Okay, you can go back through this later, but it's not, don't think about Z too hard. Just think about Z as the probability that, just think about Z as the pi, just the weighting functions. And it allows us to just write now a simpler probability, and we can write that, we can write the conditional probability of X on ZK, and we can write the marginal probability of just ZK. Okay. And then, let's talk about self-assignment really quickly. So what is the probability of data point X in each component? So we have 3 components here. How many components do we have here? 3. How many probabilities? 3. And what is the sum value of each of the 3 probabilities for each data point? So for each data point X, you're going to basically sum some probabilities that it's, you know, that you'll sum like the probability that it's in this cluster plus the probability that's in this cluster plus the probability that's in this cluster. And that's going to give you the probability of like data of X altogether. And you have like sort of specific probabilities that X is in each different cluster.
Mm-hmm.
And so now we're going to think about how to calculate the probability of data points in a specific component. So let's say we want to calculate the probability of data points in the first component. So this Gaussian here. What we're going to do is we're going to calculate a value called the responsibility. And the responsibility is, so we think about the responsibility as how much of the first component is accounting for what we have, the X that we have. So you can kind of think of it as like the probability of ZK that I assign, the probability that I assign to the first component, given that I have an observed value X. So how much of X, or how much of the first component of this Gaussian is responsible for the fact that I just got this X. And so we'll call that tau 0. And so here, this is just a conditional probability. So we're saying, okay, what is the probability? So this top part is the probability of basically X being in the 0th cluster, right? So that's this top part. So that you have just this portion here divided by everything, the total probability.
Yes.
And so that is that can be written as the probability of X given X0. So like we've assigned to the first cluster times the probability of X0.
Mm-hmm.
So remember these map to kind of, so this this probability density function maps to this, and this pi maps to this, as we talked about here. So these are mapping to those. And then on the bottom here, it's still the full probability. So we're just summing everything over. And so we're just like doing some simplification now. And so we know that earlier, as we talked about, this part here, this top, the numerator is just the joint density of X and Z0. And the bottom is just the sum over all Ks of Pxk, of the joint distribution as well. And then the joint distribution over all Ks is just the probability of everything. And the top is the joint distribution, that remains the same. And from the earlier probability sort of recap that we did, we know that this is equal to the probability of ZK given X. So basically, when we have a data point X, an observed X, how much can we say, what's the probability that it's related to this first, like Gaussian, and it's related to this first cluster? Yeah, so here it says, given data point X, what is the probability that that data point is in component 0? Okay, and then if you have 100 data points and 3 components, the size of tau is 100 by 3. So this is kind of just getting at some of the multi-dimensionality of this. But I think it's easier to just think about it as like one or like individual things to start off with before you add sort of dimensionality.
And so since X is a vector, we end up with a vector of probabilities.
Yeah.
Okay.
Yeah, and so remember we called this the responsibility, and it's a very, I think it's a very apt name because you can think, okay, how much is this Gaussian responsible for this observed value that I see? So responsibility tau.
Oh shit! I see what's happening next. Okay, go ahead.
Okay, and then so then we want to like kind of, so then we can do this for like all the different Gaussians, right? All the different clusters. So we have representations of the joint probability. So ignore this like theta. I don't think it's really that useful. So just we have the joint probability px at znk, and the marginal probability px. So okay. I guess znk is the probability of, or the latent variable at point latent variable at point n, or I guess dimension n.
Sorry, Nosa, your mic turned you into gremlin voice again.
Can you hear me? Can you hear me?
Yep.
Yeah.
Okay. Okay, so we have representations of the joint Px, Z, and K. I'm trying to remember how to describe this Z and K really quickly. So we know that X is like X1. No, that's dimension. Yeah, okay, so so we have different x's. So if we think of like a big X, then we have like x1, x2 to xn, and each of these have dimension d. And so each of these x's is going to have like k, basically kz's that describe the probability that they're assigned to those like k clusters. Does that make sense? So that's what this znk is. It's like each of these x's have like an n from like their subscript, and then the probability then that they're assigned to the kth cluster. Okay, and so then the conditional probability of z and k given an x can be derived using Bayes' rule. So we basically just did that up there, but I'll kind of show it in detail here. So responsibility that a mixture component takes for explaining an observation x, as we talked about before. So tau znk is equal to the conditional probability of znk given x, and that's equal to, using sort of Bayes' rule, probability of znk times the probability of x given znk, and summed over all of the probabilities, right? Divided by sum over all the probabilities. And we can write that as the probability, we can write that as the weight at k times the Gaussian at k divided by the sum of all the Gaussians and their weights. Okay, so that's a responsibility. So yeah, I mean, it's kind of intuitive. It's like, you know, how much is this Gaussian responsible? And then you divide that Gaussian and its weight divided by all the other Gaussians and their weights. And then what's the probability of picking a mixture component? Let me see what this saying. What's the probability of picking a mixture component basically, yeah, what's the probability of picking a mixture component, a Gaussian model, and picking data from that specific mixture component? So probability of PZ and Px given Z, and so that is just the product of Pz x given Z times Pz. And so that is why we call the Gaussian models, or the mixture of Gaussians, a generative model, because we're putting together all these sort of joint distributions, or we're putting together all these Gaussians into a joint distribution. And another way to think about Z here is that Z is kind of like a hidden variable. And so we can kind of think that in the real world, there's actually some ground truth, but we don't actually know what the ground truth is. So we're sort of modeling it, but there is a reason why there is a ground truth that says, okay, Z is one from or we can kind of think of it as this. I don't know if it's actually true that it's a ground truth. It's kind of philosophical, but I kind of think, okay, I kind of using my fridge example earlier. There's a truth that either I got it out of the fridge or I didn't get it out of the fridge, right? But we don't know what that truth is. Let's say we just don't know. And so Z is latent, and it describes sort of a probability that I got it out of the fridge, but we know that there's actually something that exists as a ground truth. So that's kind of a way to think about Z as well. It's like, okay, we don't actually know what it is, but we have some probabilities that describe what it can be from our model. Okay, and then this is kind of doing some of the same stuff. I'm not really sure why there's an extra slide on this, but just kind of to confirm our understanding, the Gaussian mixture model parameters are the means at the different Gaussians, the variances at different Gaussians, and the probability, basically, or the weight at the different Gaussians. And so here, so this is like the conditioning, right? So they're using this theta, he's using this theta as just saying that, okay, this is the conditioning on these variables of on these parameters. And so so if we go back, yeah, I won't, okay, yeah, never mind. Yeah, I don't fully understand the theta, but it seems like he's sort of basically thinking of it as like these theta parameters, these calculation parameters.
Lost you again.
Yeah, you're back in grandma mode. Sorry, fam.
You gotta invest in some AirPods, my guy.
It's funny because you probably
now?
definitely will. We can hear you now.
Yeah, I think it's my computer actually, because it still does it even if I don't have headphones in.
Oh.
Yeah. And I don't know how to solve that. So yeah, so if we know that data consists of a few Gaussians, and we want to like fit, so let's kind of going back to the example earlier, we want to fit parametric models. So we basically want to find out what is going to be the mu k and what's going to be the sigma k and what's going to be our weights here. We can do that. And so here's what we're going to do. So we know that the density model may be multimodal. It might be a so we can model it as a mixture of unimodal distributions, unimodal Gaussians, and we will consider a mixture of k Gaussians. And so the way we're going to do this is we're going to learn these three parameters. We're going to learn pi k, we're going to learn mu k, and we're going to learn sigma k. And then a note on these sort of latent variables. So a variable can be unobserved or latent because one, it's an imaginary quantity meant to provide some simplified and abstractive view of the data generation process. Two, it's a real world object and or phenomena, but difficult or impossible to measure. For example, the temperature of a star. Object or phenomena, but sometimes wasn't measured because of faulty sensors. So basically, you know that these things exist, these latent variables like exist, but you didn't observe them, and you don't know what they actually are. So discrete variables can be used to partition cluster data into subgroups, and continuous latent variables can be used for dimensionality reduction or factor analysis, etc.
What three variables are we learning again?
Say that again?
What three parameters are we learning?
So we're going to learn pi, mu, and sigma for each of the modes.
Okay, thanks.
Okay. And so there's some recap here. We will skip that. Actually, we'll skip it up to here. So now we're going to. So now we're trying to learn these. So we have some data, and we're trying to learn the Gaussian mixture model. And so what we're going to do is, I think you first assume the k modes. So you basically are like counting, you look at the data, you count the different modes that you have. And then what we're going to do is we're going to write the likelihood function for the modes. So the likelihood function is going to be, and so if we go back to, I was going to go back to our probability lecture where we did maximum likelihood. So remember, the likelihood function is a probability of like all these. So we basically are looking at the probability of all these x being basically every single possibility it can be. And so we assume that they're independent and identically distributed random variables from the observations that we have. And then the likelihood is just the product of all the probabilities, right? And so for this one, we were using the Bernoulli distribution. And so we have here the likelihood is the product of all the probabilities, and then we write that as this. And we can write that as this here at the bottom. So we can write that as this. And then we took the log so that we don't have this multiplication. So now we have a sum. So we took a log of both sides. So we have log likelihood is equal to the log of so so I guess from this up here, we simplified it to the sum, to the p raised to the sum of all x's, because remember, when you're multiplying exponents, you can just sum them up, and same here. And so now we have the log of p times the sum of xi, and the log of 1 minus p times the sum of 1 minus xi. And then using that, we optimize P by taking the partial derivative, the partial derivative of the log likelihood with respect to P, and setting it equal to 0, and then optimizing for what P would need to be for that to be maximized. Okay, so then we're going to do the same thing with our Gaussian distributions. So the likelihood function is just the product. So we're assuming that these are independent and individually distributed. Independent and identically distributed, independent and identically distributed. And so we can write the probability of basically all our observations as the sum, the product of all the likelihoods. And we know that each px, basically each px, pxi, right? Each joint probability here is a sum of the Gaussians. So yeah, here. So each px is a sum of Gaussians. And so here we've written this as like a product of all the px over all the variables xi, and for each xi we have a sum of Gaussians, and so that's what this second part is here. And so then we take the log of that, and so the log likelihood then gives us the log of, so then we have the sum over the log of these sums of Gaussians. So you can kind of like go through the math and do that, but like this is the form of the log likelihood. And I think in the book you'll see it written as ln here, but log ln is the same thing. And so now with this log likelihood, we're trying to optimize, remember, for 3 parameters. The mu's, or we're trying to learn these 3 parameters. We're trying to learn mu, sigma, and pi. And so we can take the partial derivative of the log likelihood with respect to the mean, set it equal to 0. Take the partial derivative of log likelihood with respect to sigma, set it equal to 0. And take the partial derivative of the log likelihood with respect to pi and set it equal to 0, and solve for what those will be. So let's do that. Okay, so here's just another, I think it goes through it again. So basically showing, that the probability of all these independent variables is the product, and then each of those is the sum of Gaussians, and so you write that as this, and then you write that as this, and the log likelihood is this. Okay. Same thing again. Use a method called maximum likelihood estimation. Yeah, where I just showed you. Okay, so I'll move through that, and then this is the same result again. Okay, so now let's do optimization. So now we have the log likelihood here is equal to this. This is the form of log likelihood. And here I think they've just like written out, instead of whatever we had before, you actually write out the parameters pi and then each of the normal distributions. And so we take the partial derivative of that with respect to mu, and I'm really not going to go through the math. I'm just going to show you what the what the result is, because I haven't like had enough time to think about the math. But yeah, basically, if you take the partial with respect to mu, you'll get this form here, and then you set it equal to 0. And when you set it equal to 0, you'll see that this part here is just equal to the responsibility that we calculated earlier, this tau. And yeah, so this part of the sum is just equal to the responsibility. And so if you calculate all the responsibilities, you'll basically have this. So we kind of like are assuming that we know the responsibility, even though we don't at this moment. But if we set that equal to 0, then we can calculate mu just as represented as the sum of the sum over n of the responsibilities and xn divided by the sum of the responsibilities. Okay, so yeah, a lot of math. You need to go through it. I'm not going to go through it. And then we can optimize the covariance also by taking the derivative of this log likelihood with respect to the covariance matrix, and we get this. So this is also based on the denominator here is also the sum of the responsibilities at each k, or sum of the responsibilities over all the variables. And then you also have in here, you're going to use the calculated mean from here as an input to calculate your covariance matrix. So it's really important that you calculate this mean first and optimize this mean first before you optimize this. And then the optimization of the mixing term, pi, you take the derivative. Oh, actually, this is a little different. So here we're using optimization with Lagrange multipliers. So, so this is constrained. So the reason why we do this is because we know that pi, we know that the sum over all k of pi k is equal to 1. And so we have a constraint on our optimization. And so we can't just optimize, we can't just take the partial derivative with respect to pi. So we're actually doing some constraint optimization. And for the Lagrange I guess function is given as the function that you want to optimize, plus lambda times the constraints. So the constraints. There's lots of videos about Lagrange multiplier or constraint optimization with Lagrange multiplier, so you can kind of look this up. So you can see here, the function that we want to optimize is the log likelihood, and our constraint is given by just this sum minus 1. So you basically put them on the same side and you add that in as your constraint function. And then you take the partial derivative of the Lagrange equation, I think with respect to the thing that you want to optimize for. I'm not sure about this. I think so. Yeah. No. You take it with respect to. Yeah, you take it with respect to the thing that you want to optimize for, because you're going to set that equal to 0. Yeah. Yeah. So you would do this. So you basically take the derivative of this with respect to pi, and you would get this. Set it equal to 0, solve for the Lagrange multiplier, and then you get your pi is equal to the sum of the responsibilities divided by n, the number of data points that you have. Okay, so as a summary, they've used nk to represent the sum over all n of the responsibilities. And so these are, I guess this was down here. I should have looked. These are the sort of equations that you need to calculate the learned parameters. So yeah, let me just look up in case you don't remember this. I'm sure we've all seen these Lagrange multiplier optimization before.
No.
Oh, you haven't?
No.
What? You saw this in like math, like 42 or something.
We took CME.
Oh, well, you probably saw it in CME.
No.
It's
Kevin.
just, yeah, we have, I think, but it's just, you probably forgot it. It was so minor, but it's pretty easy once I could send something about Lagrange too.
Well, it looks
Yeah.
very straightforward. Like I get what's happening. So thank you for walking us through it. But fuck no, I didn't see it.
Yeah, there's some nice Khan Academy videos and stuff that you can use. Okay, so let's wrap up here. So the expectation maximization algorithm. So basically, it's kind of like k-means, as we talked about when Stuart was lecturing. There's like expectation step, and then there's a maximization step, and you just kind of keep going until you converge. And so the expectation step, we select. I should write here. So you select values for pi, k, mu, k, and sigma k. So you have some initialization, right? So you initialize these values, and then you calculate the responsibilities using those values. And then in M step, you use the actual data, right? So you use the actual data, xn, that you have to calculate mu, sigma, and pi. So then for the expectation maximization, you do it in 2 steps. So first you fill in hidden values using inference. I'm not sure what that actually means. But what I read is that you basically just initialize those values, and then you apply the maximum likelihood estimation to estimate the parameters. And the expectation maximization is always going to converge to a local minimum of the likelihood, as we sort of proved with k-means last week. That's another expectation maximization algorithm. I think there's something else I want to say about this. So one of the examples that I think, or one of the things that I think you mentioned last week, Stu, is that k-means, or I think maybe Kevin mentioned this, like k-means is usually used as like a starting thing to like something else. So this is like one of the something else's that you can use k-means as a starting thing. So you can use k-means to basically get some clusters, and then the center of your clusters, like you'll use as your mu k, and then you can, and there's probably other ways to like come up with, the pi k and the sigma k, or actually you can figure out the sigma k's based on those clusters that you've created using k-means. Oh, and then the pi k's can be, so for example, let's say you had 2 clusters or something from your k-means thing. Then you can say, okay, pi k, so this is k1 and this is k2. And so you can say pi k or pi 1 is equal to the number in k1 divided by total number. And so pi 2 is equal to the number in k2 divided by total number. And then mu k is the center from k-means. And then you can calculate sigma k as like, using that cluster variance, I guess covariance from cluster data. So that's a wise way to initialize, so you're not just like blindly initializing. And then here is an example of it happening. So it seems like first you have some big clusters, and after the first iteration, kind of, so you can see these like you can see that you have like some sort of like percentages and some probabilities that each one of these points is in the different clusters. And that's what's represented as like sort of these circle graphs inside each one. In the book, they have like sort of mixtures of colors, but I think this also represents it. And so you can see after the first iteration, the probabilities are updated, and then you keep going, and you keep going, and you start to cluster. You start to increase the probabilities and change them, and then you keep going, and it's converging, and then it kind of converges after the 20th iteration. So I guess to reiterate, given a Gaussian mixture model, the goal is to maximize the likelihood function with respect to the parameters comprising the means, covariances, and covariances of the components and the mixing coefficients. So you initialize the means, covariances, and coefficients, and evaluate the initial value of the log likelihood. And then in the expectation step, you take basically the expectation of the that each x is assigned to a certain Gaussian, and so basically this is the responsibility. So here they're using a different variable gamma, but so you calculate the responsibility, and then you use that responsibility in the M step to estimate the parameters. And then you evaluate the log likelihood. I guess this is like a final step. So you evaluate the log likelihood to, I guess, to see if it's less than or if it's higher than your previous one. Yeah, so yeah, that makes sense, because there's no way that you would converge then if you didn't evaluate it. So you would evaluate it in each step to make sure that it's continually getting, the likelihood's kind of getting higher as you are as you're continuing, and then at some point you'll get to convergence, or you have some bound that you say, okay, when you're over this bound, we're good. Or when the difference between the log likelihood for this step and the previous step is between a certain threshold, then we can stop. But if there's no convergence, then you keep going. You return to the E step and so on.
It seems like the log likelihood is the distance function here, and we're just maximizing.
Yeah. I mean, does that make sense? Like, the reason why we're evaluating it, it's to make sure that it's increasing.
Yeah.
Right? Yeah. Okay. Yeah. So relationship to k-means. K-means makes hard decisions. Each data point is assigned to a single cluster. GMM/EM makes soft decisions. So EM is actually, generally expectation maximization is kind of like a general algorithm. So really, this is a special case of expectation maximization for Gaussian mixture models. And k-means is also another special case of expectation maximization. So you can kind of abstractly think about expectation maximization in a general form that's written as this. So you have some thing that you want to maximize, you initialize parameters that you care about, and then you evaluate that based on those initialized parameters, and then you construct some likelihood objective that you want to maximize, and then you kind of keep checking for convergence and keep going back and doing it until you get what you want. Not quite sure what this is. Jensen's inequality. Yeah, I mean, I feel like this is just some theory about EM algorithms that maybe says that they'll always converge. I don't know. It doesn't seem that important. So we'll just skip it. Okay, so we are basically done. So the take-home messages is there's sort of a generative process of creating these Gaussian mixture models. And so you infer cluster membership based on a learned Gaussian mixture model. And the way you learn that Gaussian mixture model is through expectation maximization algorithms for Gaussian mixture models. Okay. Yeah, so I think I was talking to Kevin yesterday, and he was saying that like he spent a lot of time like studying these Gaussian mixture models to like really understand them. And I think that like that kind of is what is required, because like you have a lot of math, you have a lot of probability in here, and like I think like from a conceptual level, like I think this lecture, or at least for me, I don't know about for y'all, but hopefully for y'all, but this lecture kind of gave you an understanding of what what these are. But a lot of the math and the actually implementing will help you kind of solidify and use it when you feel it's needed.
It makes sense to me. Yeah, it's pretty deep.